11.5 or and problems. So those two words, or and, we have been talking about them since chapter 2. And here they're coming back again. Remember, and or, they mean something. Or is a little loose. It's one or the other. I'm not really, it could be both. That's fine. And is very strict. That means both have to be true, that both things have to happen mutually for something to happen. So we're going to talk more about or and today. Or problems. The or probability problem requires obtaining a successful outcome for at least one of the given events. The probability of A or B. A or B equals P of A plus P of B minus P A or B. All right, so we have example 1, each of the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's written on a separate piece of paper. The 10 pieces of paper are then placed in a hat, and one piece is randomly selected. Determine the probability that the piece of paper selected contains an even number or a number greater than 6. So let's use our formula. Let's set it up. Our first part is P, A, or B. So we're just setting up like what are we actually looking for? So we're looking for the probability. So probability. We have that a piece of paper selected contains an even number. That's our A. You can also just write E. You don't have to write even. You can write E. And then we have or a number greater than 6. So you can literally write out a number greater than 6. I mean, like literally write out that phrase, those words. Or you can say greater than 6. Okay, and that's our B. So first, let's just break down each piece. Let's break down A, because remember, P of A, we said that that's going to represent even numbers. So let's count all the even numbers 1 through 10. So we have 2, 4, 6, 8, and 10. So if you think, we have 1, 2, 3, 4, 5 are even. And that's 5 out of the total. So 5 out of 10 are even numbers. Then we're going to add that to B. B, remember our probability of B, we said that's a number greater than 6. So let's check off all the numbers greater than 6. They have to be greater than 6, not 6. So that's 7, 8, 9, and 10. Those are all numbers greater than 6. So if we look, we have 1, 2, 3, 4. 4 of them are greater than 6. So we have 4 out of 10 are greater than 6. However, this is asking for or. If I look at the numbers that have double check marks, like this one and this one, that's not or. 8 is even and greater than 6. 10 is even and greater than 6. It's not looking for and, it's looking for or. So those moments that we have double check marks, that's telling us we're not allowed to count those because that's an and equation. We're not looking for and, we're looking for or. So we know 8 and 10, those two numbers, they're even and greater than 6. We're not looking for and, we're looking for or. So we actually need to take out 2 out of 10 of those numbers. That's what this part is. Anytime that you have a double check mark or an and situation when we're actually doing the probability of A or B, we exclude it only when we have to. In this case, we have to because we have a double check mark. 8 and 10 are even and greater. From here, we simplify. 5 plus 4 is 9. 9 minus 2 is 7. So that's 7 over 10. And we cannot simplify that. That's just it. 7 over 10 is 7 over 10. Mutually exclusive. Two events A and B are mutually exclusive if it is impossible for both events to occur simultaneously. If two events are mutually exclusive, then P, A, and B equals 0. So mutually exclusive, I'll give an example of that it's impossible, daytime and nighttime. It can never be daytime and nighttime. That's impossible. It's either daytime or it's nighttime, or I can't say rainy and sunny because we have rain showers here, but or sun showers here. But you get me. Mutually exclusive is when it is impossible to happen. All right, so we have another formula when we don't have to exclude anything. It's the same formula except no minus. PA or B equals PA plus PB. So we only have to use the minus part, the part circled in red, if there's a part where it says and. If it doesn't have an and situation like we have in 8 and 10, you don't need to take out anything. And we're going to practice that through example 2. So one card is selected from its standard deck of cards. Determine whether the following pairs of events are mutually exclusive and determine P, A, or B. Alright, so mutually exclusive means that it doesn't affect the outcome, meaning there's no and situation. So if we look at P, A, or B, for A as an ace, so we have A that represents an ace, so we have the probability of an ace, or, and then our B, we have a 9. So we can just say 9. Now look up your formula sheet or go back to early parts of chapter 11 to look at your deck of cards. There is no part of your deck of cards that's an ace and a 9. It will always be, always, you will either get an ace card or a 9 card. Always. Those never ever are on the same card. So because we know that these two cards are completely different and there's never a 9 ace or an ace and a 9, it's always an or, we know that this is mutually exclusive. Meaning the ace doesn't mess with the 9 and the 9 doesn't mess with an ace. It doesn't affect it at all. So what we're going to do is count how many ace cards we have. We have 4 out of 52 ace cards. Then we're going to add that to how many 9 cards we have. We actually have 4 out of 52 9 cards. Look at your deck of cards in the formula sheet. 4 plus 4, we get 8 over 52. 8 over 52 is 2 out of 13. Now, there's actually a reason why that's 2 out of 13. If we go back to our deck of cards, you'll see we're looking for an ace or a 9. Let me just write here what we remember what we were looking for. An ace or a 9. So let's look at all of our aces. We have 1, 2, 3, 4. Awesome. Our 9s, we have 1, 2, 3, 4. But do you notice that each of these, they all have the same group? It's ace through king. It's just a different symbol and a different color. That's because we have 4 sets. We have a set of hearts, a set of clubs, a set of diamonds, and a set of spades. So if all the cards are the same in each set's going to have an ace and a 9. So if we just break it down to one set, let's break it down just to the spades. Let's break it down and just look at the spades. If we look at the spades, there's 13. There's 13 cards. And do you notice 2 out of the 13 are an ace or a 9? And isn't that our answer? Interesting, right? You are allowed to use your deck of cards to answer these questions. All right, let's go to B. We want to know the probability of an ace or a heart. All right, as always, we're just going to go based off of each piece. So our first piece is A. So the probability of an ace, remember there's 4 out of 52 aces. The probability of a heart card, all of our heart cards, if we look at all of the hearts, 13 of them are hearts. So 13 out of 52 are heart cards. However, we have heart cards that are aces. We have 1. So this is not mutually exclusive. It is not mutually exclusive because we have an ace and a 9. So we actually need to take something out. We need to take something out because there's an ace That is a 9 card. If we go back to our deck of cards, we're looking for an ace or a heart. If we look at all of our heart cards are right here. We want or. This is not or. That's an and. That's an ace and a 9 card. So we're not allowed to have that. Since we're not allowed to have that, we need to take it out. So since we know we need to take it out, we only need to take out 1 out of 52 cards. Only one of them is not allowed. So because of that, we can go ahead and keep simplifying. 4 plus 13 is 17. 17 minus 1, we get 16. So that's 16 over 52, which we can simplify because they're both 16 and 52 are divisible by 4. So we can divide by 4. And when we divide by 4, we get 4 over 13. So I want you to take a moment, pause the video if you're feeling like you can. If not, it's cool. But pause the video and see if you can do C. I hope you did. I hope you tried. If not, that's okay. Maybe you're not ready. Let's do it together. So we want to know the probability of a red card. So I'll just put R. Or a black card. I'll just put black. Do you notice if it starts with an A, I write it out? If it starts with a B, I write it out because I don't want to get ace and A mixed up. I want to keep it consistent so we all know what we're talking about. Okay. If you think about it, every card in the whole deck is red or black. The entire deck is red or black. When we say these things, the entire, the whole, all of it, all that means 100%. We know 100% equals 1 because all probability happens between 0 and 1. 0 is 0%, 1 is 100% because remember percentages are just decimals in between 0 and 1. So you will always get a card that is black or red. There's no, and don't say jokers because we say 50 a standard deck of cards. So we take the jokers out. So the entire deck is red or black. Alright, part D. We want to know the probability of a picture card. Picture cards are the ones with the faces, Jack, Queen, King. So, in part C, I didn't mean Jack, I meant Joker. J's and J's, they got me confused. Anyways, in part D, we have the probability of a picture card. So I'm just going to put picture, or pick, or a red card. Alright, if you look at your deck of cards, there are 12 picture cards. 12 out of 52 are picture cards. If we look at our deck of cards, red, half of them are red. Half of the entire deck is red. So there are 26 out of 52 red cards. However, there are picture cards that are red. If we go back to our deck of cards, we're looking at our picture cards. Our picture cards are these ones right here. These are our picture cards. If we look, we have some that are not allowed. We have this one's red, 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 this one's red. We have 6 that are red and picture cards. We're not allowed to have those because we're looking for or. Those 6 are and. So we need to take them out. So we need to take out 6 out of 52. And since we're taking out, that means it's not mutually exclusive. Anytime you have to exclude values, it's not mutually exclusive. Alright, let's simplify. So 12 and 26, that's 38. 38 minus 6 is 32 over 52. We can simplify by 4. Most of the time you can actually divide by 4. You want to know why? Because there's 4 groups. There's 4 sets. There's hearts, clubs, spades, and diamonds. There's a 4 sets. That's why we usually divide by 4. And when we divide by 4, we get 8 over 13. With replacement, when a unit selected at random from the population is returned to the population, and then a second element is selected at random. Basically, what that's saying with replacement is, say you have a bag of marbles, and you take a marble out. That means you put it back, and you can pick it again. Without replacement is just the opposite. When a unit is selected at random from the population, it is not returned to the main lot. Meaning, you have a bag of marbles, you pick one of the marbles, and you put it on the table, you can never pick it again. And probability problems requires obtaining a favorable outcome in each of the given events. So A and B equals P of A times P of B. Remember, and is multiplication, or is addition and subtraction. Since we multiply to find P, A, and B, the formula is sometimes referred to as the multiplication formula. When using the multiplication formula, we always assume that event A has occurred when calculating P of B because we're determining the probability of obtaining a favorable outcome in both events. So basically what this is saying is that when we do theoretical probability, we're just assuming, we're theorizing what's going to happen based off of the information we have. It could not happen. It's probably going to happen at this rate. So when we do and, we're just assuming the first thing is happening, therefore the second thing can happen. All right, example 4 and 5. 2 cards are selected with replacement from a deck of cards. Determine the probability that 2 spades will be selected. And example 5. I know, why are we reading the next example? You'll see what I mean. 2 cards are to be selected without replacement from a deck of cards. Determine the probability that 2 spades will be selected. So these are actually the same question, except one word is different, with and without. So we're going to see with replacement and without replacement how it actually affects our probability. All right, we're picking 2 cards. So here's our first and our second. You see how already it's so different from or, because it's not saying find the probability of A or B. It's just you're picking 2 cards. It's not asking what to pick. Now that we're picking 2 cards, it's going to get more specific with replacement. Let's go ahead and determine the probability that you get 2 spades. So we need to determine, first of all, the probability of a spade with replacement. So I have a fresh deck of cards. It's never been touched. I just took the jokers out. I have 13 that are spades. 13 out of 52. Alright, I pick a card. It's a spade. Because it says with replacement, I put the card back in the deck. If I put the card back in the deck hasn't changed. For my second pick, I still have 13 out of 52 to pick from. Alright, we're going to multiply. So 13 times 13 is 169. 52 times 52 is 2,704. We can simplify this down into 1 over 16. Look on Canvas under announcements on calculators with fractions. It's in the chapter 8 announcement. I show you how to simplify that with your calculator. Alright, let's do the other one without replacement. So it's the same setup. We still have 2 cards. But this time we're saying without replacement. So our first pick never changes. It's a fresh deck of cards. It's never been touched. I just took the jokers out. So there are 13 out of 52 spades. However, this is without replacement. So what that's saying is I picked a spade. My first card on top was a spade. It just so happened. I pick the card. I put it on the table. The deck is changed forever. The deck now has 51 cards left. And if I already picked a spade, there's only 12 spades left. So because it says without replacement, what we did is we took one spade card out. We don't put it back in the deck. Since you don't put it back in the deck, you have 51 cards left and 12 of them are spades. We can go ahead and multiply because this is not or problem, it's and. So 13 times 12, we get 156. 52 times 51, we get 2,652. We can simplify this into 1 over 17. Again, look at the Chapter 8 announcement with the calculator title, and that will show you how we can do this with our calculator. Independent events and dependent events. So event A and B are independent events if the occurrence of either event in no way affects the probability occurrence of the other event. Rolling dice, tossing coins, those are examples of independent events. Because if I toss a coin, I can't say, okay, take the heads out. It's always going to be there. Or if I roll a die, I can't say take one out. It's always going to be there. So another way to remember independent events, that is with replacement. As well, with replacement is generally independent because if you put it back, it doesn't change the deck of cards. If I pick a marble out of a bag and put it back, the bag stays the same again. Dependent events is just the opposite. Two events are considered dependent if the occurrence or outcome of the first event changes the probability of the next event occurring. In general, in any experiment in which two or more items are selected without replacement, the events will be dependent. So without replacement just means dependent. 100 people attend a charity benefit to raise money for cancer research. 3 people in attendance will be selected at random without replacement, and each will be awarded one door prize. Are the events of selecting 3 people who will be awarded the door prize independent or dependent? So you probably already saw the key phrase that you're looking for, without replacement. So that should automatically ding 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 in your head. That is dependent. Now, what if it didn't have that phrase without replacement? How would we know for sure that this is a dependent event? So the events are dependent since each time one person wins, they cannot win again, and it changes the outcome of who wins next. So we're picking 3 people. So let's say I win. I'm the first out of 100 people who wins. I can't be picked again because I can't win twice. That's not fair. So now there's 99 people left over. I changed the outcome. I changed from 100 to 99 people. Let's say my friend wins. Now there's 98 people to choose from. So you see how we're changing the amount of people we're allowed to pick from? That's another way to say dependent. So when would we use all of this probability with dependent, independent, stuff like that? Well, it has to do with like drug trials and how we say, okay, like let's bring this drug onto the market so everyone can take it. So this is like stage 1 trial right here. How do we go to mass population? So, a new medicine was given to a sample of 25 of Dr. Nick's patients with the flu symptoms. Of the total, 19 patients reacted favorably, 2 reacted unfavorably, and 4 were unaffected. 3 of these patients are selected at random. Determine the probability of each of the following. So we're picking 3 people. Let's determine all 3 reacted favorably. All right, so we're picking 3 people. So we set it up our first, our second, and our third. Now let's bring out the favorable people. 19 reacted favorably. And total, we have 25 people total. So 19 out of 25 acted favorably for the first pick. We haven't picked anybody. It's a fresh pick. So we actually have 19 out of 25. Now, this is not an or problem. There's no or word in here, so we don't care about plus or minusing. We times. Okay, we pick someone. Now, there are 18 favorable people left out of 24 people because we pick someone. We can't pick them again. When you're doing a study, you can't pick the same people twice. That's not fair. So we picked another person. That means 17 favorable people are left, and there's only 23 people left to actually choose from. We're going down each time we pick because we can no longer pick that person. We're taking the marble out of the bag so we can't pick it again. 19 times 18 times 17, we get 5,814. 25 times 24 times 23 is 13,800. We can simplify this again. Check your calculator in chapter 8 to figure out how to do that. When we simplify this, we can get 969 out of 2300. So we still have 3 patients we're picking. So our first one is the first patient acted favorably, so that's 19 out of 25. The second one reacted unfavorably, so 2 were unfavorable, but that's out of 24 people now because we already picked a person. Then our third pick is unaffected. So unaffected, it's 4 were unaffected. So 4 were unaffected. Now we have 23 people left. So 19 times 2 times 4, we get 19 out of 1725, which is about 0.0110 or 1% of the time. Because that's very specific things you want, right? I want the first to be favorable, the second to be unfavorable, and the third to be unaffected. So those are very, very, very specific parameters. So that's why it's 1%. Alrighty, part C, no patient reacted favorably. So, no patient reacted favorably, so that's the rest of them. So, not favorable, we have 2 that were unfavorable, and 4 that were unaffected. So those are not favorable, technically. So 6
weren't favorable. So that's how many we have now. So we're still picking 3 people. So at first we have 6 out of 25 people. Then we have 5 out of 24 people. Then we have 4 out of 23 people. And when you multiply that together, we do 30 times 4, which is 120. And then 25 times 24 times 23, we get 13,800. We simplify that. So we get about 0.00869566, which in percentage is 0.0087% of the time. Alrighty, part D. At least one patient reacted favorably. Isn't that the opposite of not favorable? Isn't that the opposite of not favorable? So we're talking about the opposite of not favorable, which we have that. We have that number. Unfavorable is 120 out of 1380, so that means favorable is the opposite. So we're just going to subtract the totals. If those are really big numbers, try to simplify. So you see how they're both 0? That means we can simplify these. We can. And we can actually simplify this down into 1 over 115. So favorable, that would be 114 out of 115. Because what you do is you do 115 minus 1 right here, and we get 114. So favorable is 114 out of 15, which is about 99%. But doesn't that make sense though? Because wasn't 1%? This is from part C. And isn't that about 1%? About, right? So that means about 99% reacted favorably, because it's the opposite.